The canonical probabilistic model for temporal or sequential data is what's called a Markov model, and Markov models are named after Andrei Markov, who was a Russian mathematician who did some work in stochastic processes in the late 1800s and early 1900s. And if I'm not mistaken, this photograph was taken right after Markov won the prize for the world's pointiest beard. So what are Markov models? The idea behind a Markov model, it exploits a very sort of deep, intrinsic fact about the real world, and that is that the future is independent of the past given the present. The future is independent of the past given the present. In other words, if you know the exact state of the world right now, and you wanted to use that knowledge to predict the future, then knowing something about the past, about the state of the world 1 second ago or 1 day ago, is not going to help you predict the future, because you know everything that you could want to know is already encoded in the current state of the world. So this is true at least in the sort of classical Newtonian view of the world, and I don't really know enough about quantum theory and all to know whether this is true in that setting. But it's at least true. It's hard to sort of imagine how this couldn't be true once you get your head wrapped around what this means. And so, because at least on the large scales, this is a fundamental fact about the world, Markov models can be used to model an extraordinarily large number of applications. So whenever we're using Markov models, we're thinking about temporal data, or some sort of sequence of data. So for example, some things for which Markov models can be or are used would be like weather, or economic data like in finance, language. Markov models are often used for language, music, even music, just a whole litany of things. So I could go on and on the list of things that Markov models are used for. So I wanted to give you a couple sort of real examples of applications of Markov models, things for which they're used. So I use a speech recognition software called Dragon Naturally Speaking, and let me demonstrate a little bit for you here. Speech recognition software programs use Markov models to listen to the sound of your voice and convert it into text, period. So you can see, well, I guess it got most of it right, but it messed up here at the end, and verdict intertext. So it's not perfect, but these programs work quite well. And this actually, it would probably do much better, except I'm using a new microphone right now, and I haven't trained it on the new microphone. So that's one application. So Dragon Naturally Speaking, I don't know all details of their implementation, but I think Windows Speech Recognition uses Markov models to model what you're saying. So that's one sort of application of Markov models. And let me give you another one here. Markov models are also used to generate music, so musical compositions. And let me play here. I downloaded a little clip of a composition that was generated. I'm not sure if it was generated using a Markov model, but they do use Markov models for this type of thing, and this was an interesting example of automatically generated music. So here it goes. Okay, that's a little bit of it. I'm going to stop there. Hopefully you could hear that. Hopefully it wasn't too quiet. So those were a couple of applications, and one other, just a sort of really entertaining one is if you want to look up for language an example of a Markov model that was applied to generate language. If you look up Mark V. Shaney on Wikipedia, an entertaining entry in Wikipedia there. So let me now give you a little bit more concrete examples of some data that we might be interested in modeling using Markov models. And we'll build up to the definition of a Markov model by just sort of exploring what we might want out of a model of temporal data. So first, let's suppose we had some data. Maybe I'll draw some axes here. Draw some axes, and let's say we got some data that looks maybe, so I'm going to be thinking about a sort of climate sort of example, and maybe this is years on this axis, years. And we get some data points that have some randomness, but there's also some sort of pattern, some sort of temporal pattern here, some sort of periodicity that is correlated with the years. Some sort of seasonal change. So for example, maybe this would be something like CO2 levels in the atmosphere. So there's this sort of periodicity, and there's also sort of a drift here, I guess, in what I drew. And this is the kind of temporal or time sequence data that you might want to use a Markov model, or a generalization of a Markov model for. Another example would be, say you're trying to design a robot, and you're using GPS coordinates to figure out where it is. So your robot's going to be driving around, and you've got latitudes and longitudes. You get a sequence of GPS points, and you want to keep track of where your robot is. So your software program so you're going to get one point here, and then maybe another point at that latitude and longitude, a third point. So over time, so this is at time 1, time 2, time 3, time 4, time 5, and these don't represent the exact position of your robot. They're sort of noisy measurements of the position. And maybe this is time t or something. And what you want to do is figure out the actual position at time t. So this is the kind of thing that you would use a Markov model or some sort of Markov model for. And one more example. So let me give you one more example. Something sort of completely different. Well, I mentioned language before. What is the word at the end of this So I'm sure you could fill in the blank here. And Markov models are often used for language to model text and natural language like this. So filling in the blank in a sense like this is something that you might use a Markov model for. All right, so those were just a few little examples. And now let's start to think a little more formally. So with these examples sort of in mind, so we get some data, right? We get some, well, let me just draw it as x1 to xn. So these would be like GPS positions or CO2 levels or what have you. And we're going to model this data. So this is sequential data now. We're thinking of it as sequential. So, well, we want to have some probabilistic model. So we may as well take some random variables, x1 to xn, to model this data. It's reasonable. I mean, of course, if we're going to use probabilities, that's the natural thing to do. But what probabilistic model should we use? Well, we could, maybe the simplest thing would be we could take them to be IID. But is that going to capture the dependencies that that we're interested in, like for example here. So with these CO2 levels, there's clearly some dependency between points which are nearby. If you're nearby in time, then your CO2 level is going to be closer also. Or maybe on average it'll tend to be closer. So the IID assumption is not really cutting it because it's saying that there's no dependencies between them. So IID is not going to work. So what dependencies matter, right? What dependencies do we really want to capture? I mean, if we just allowed everything to be dependent on everything else, then we would get a totally intractable model. So we'd like to, use have some sort of independence to make things more tractable. And what sort of dependencies matter? I knew a guy who was a weatherman. Well, he used to be a weatherman, and he always used to say that for the most accurate forecast of tomorrow's weather, look out your window. Or in other words, the most accurate prediction of what's going to happen in the near future is what's happening right now. And so that's sort of like this. There's these dependencies, and sort of like this here with the GPS. And it might not always be the same, but at least these sort of suggest, and the same thing here in the sentence, these sort of suggest that the most information, if we're looking at xn plus 1, we're going to get the most information by looking at xn, by looking at the most recent points, or maybe xn minus 1 or xn minus 2. So, but by looking at more recent data, we're going to get much more information than by looking at data from the distant past. So recent data tells you more than the recent past tells you more than the distant past. So this suggests that we could do the following. We could make xt, x at time t. So if we were designing some generative model, we could choose x1 and then choose x2 to depend on x1. And in general, we could choose xt to depend on the most recent points, xt minus 1, xt minus 2, and so on, back to say xt minus m for some fixed m. So if we were to write down, we could write down a generative model which satisfied this. And the simplest case would be m equals 1. So this is going to lead us to the definition of a Markov chain. And I'm about to run out of time in this video, and I want to make sure to give full treatment to the definition. So let me stop there, and we will come back and we'll continue talking about Markov models and Markov chains.